Please subscribe to support the channel. What happens when matter is crushed beyond the limits of atoms themselves? This is not just a poetic question. It's one of the most profound mysteries in modern astrophysics. When we think of matter, we often imagine things we can touch: stone, metal, water, or even the air we breathe. All of these are made up of atoms, the tiny building blocks of the universe. Inside every atom lies a nucleus, made of protons and neutrons, which in turn are made of even smaller particles called quarks. Normally, quarks never exist freely. They're forever confined inside protons and neutrons, bound by the strongest known force in nature, the strong nuclear force. But what happens if we take matter to the most extreme environment possible, far beyond the crushing pressures of Earth, beyond the cores of normal stars, even beyond the unimaginable density of a neutron star? Could there be a stage of matter where the very building blocks of protons and neutrons themselves break apart, creating a star made not of atoms, not even of neutrons, but of quarks alone? This is where the tantalizing idea of quark stars enters the picture. Exotic, hypothetical stellar remnants that may represent an entirely new state of matter in the cosmos. They are not confirmed. We have no direct evidence yet. But the possibility of their existence forces us to stretch the limits of human understanding, to question what matter truly is at its most fundamental level, and to confront the possibility that the universe still hides secrets even more bizarre than black holes. Now, before we dive into quark stars themselves, it's worth asking, how do we even get from a normal star, the kind we see shining in the night sky, to something so exotic and extreme? To truly appreciate the mystery of quark stars, we need to first walk through the life and death of stars themselves. Stars are often described as the engines of the universe, burning through nuclear fuel and illuminating the cosmos with their energy. Yet behind their radiant glow lies a profound story of transformation. A story that begins with the simplest elements in the universe and ends in some of the most extreme objects ever conceived by human thought. To understand where quark stars might fit into this story, we first need to follow the evolutionary journey of a star from its earliest years to its possible final fates. Every star begins as a vast cloud of hydrogen gas and dust, drifting silently in the coldness of space. Gravity, relentless and patient, draws these particles together. Over millions of years, the cloud contracts until its core grows so hot and dense that nuclear fusion ignites. This is the true birth of a star, the moment when hydrogen nuclei collide and fuse into helium, releasing vast amounts of energy in the process. This balance, gravity pulling inward and nuclear pressure pushing outward, creates the long, stable phase known as the main sequence. For stars like our Sun, this phase lasts billions of years. The Sun is quietly fusing hydrogen into helium in its core, producing light and heat that sustain life on Earth. But nothing in the universe lasts forever, not even the steady brilliance of stars. Eventually, the hydrogen in the core begins to run out. When this happens, gravity starts to gain the upper hand, compressing the core further. The star swells into a red giant, a swollen, cooler, but brighter phase of stellar life. Our Sun will one day expand so much in this stage that it could engulf the inner planets, including Earth. What happens next depends heavily on the star's mass. Smaller stars, those with less than about 8 times the mass of our Sun, cannot maintain fusion forever. Once their helium and heavier elements are spent, the outer layers drift away, forming a planetary nebula, a beautiful shell of glowing gas. What remains is the star's exposed core, which cools and stabilizes into a white dwarf. White dwarfs are incredibly dense. A teaspoon of their matter could weigh tons. But compared to what comes next in larger stars, white dwarfs are tame. More massive stars face a much more dramatic ending. When such a star runs out of fuel, its core collapses under the force of gravity in a catastrophic implosion. The outer layers rebound in a spectacular supernova explosion, blasting material across the galaxy. What remains after the explosion depends on the original mass of the star. If the core is between about 1.4 and 3 times the mass of the Sun, the collapse crushes protons and electrons together into neutrons, creating a neutron star, an object so dense that a sugar cube-sized piece of its matter would outweigh Mount Everest. Neutron stars are extraordinary in their own right, but they are only one step in the ladder of cosmic extremes. If the collapsing core exceeds about 3 solar masses, not even the incredible neutron pressure can withstand gravity's pull. The collapse continues until space-time itself folds inward, creating a black hole. In these enigmatic objects, Matter is compressed to a point of infinite density, hidden behind an event horizon from which no light can escape. Black holes are among the most mysterious objects in the universe, but perhaps what lies just short of becoming one is even more fascinating. This is where the hypothesis of quark stars enters the stage. If a collapsing star's core is heavier than what can remain stable as a neutron star but not quite heavy enough to form a black hole, something extraordinary may occur. Under such unfathomable pressures, neutrons themselves may break down, dissolving into their fundamental constituents, quarks. Instead of a neutron-rich object, what's left behind could be a star made of pure quark matter, hovering in that razor-thin space between neutron star and black hole. So, the evolutionary pathway of stars could look like this. Main sequence stars lead to red giants, small to medium stars become white dwarfs, more massive stars collapse into neutron stars, and the most massive collapse further into black holes. But perhaps, nestled between neutron stars and black holes, exists a fourth possibility: quark stars. They don't fit neatly into the traditional ladder of stellar evolution. They represent a hidden step, a bridge between the already extreme neutron star and the all-consuming black hole. The mere idea of quark stars forces us to rethink the end stages of stellar life. They imply that the universe might harbor objects more compact than neutron stars but not quite lost to the abyss of a black hole. If they do exist, they would expand our understanding of stellar evolution into new, uncharted territory, where the laws of physics as we know them are tested to their breaking point. And to appreciate how such a star might arise, we first need to examine the physics of neutron stars themselves. After all, they are the natural precursor to the quark star hypothesis, and the stepping stone that bridges normal stellar matter with the strange quark world that may lie beyond. When we reach the stage of neutron stars, we are already deep into the realm of cosmic extremes. These objects are not merely stars in the traditional sense, burning brightly in the sky. They are stellar corpses, the remnants of once mighty suns that lived fast, burned ferociously, and died in spectacular explosions. But unlike the silence that follows death, the birth of a neutron star is the beginning of an entirely new form of matter, one that pushes the known laws of physics to their limits. To truly grasp what a neutron star is, we have to retrace what happens in the heart of a massive star at the end of its life. When nuclear fusion, the process that kept the star alive, can no longer continue, gravity takes command. The core of the star collapses inward at incredible speeds. As it does, protons and electrons, once kept apart within atoms, are smashed together under such colossal pressure that they merge into neutrons. This reaction is not just a simple rearrangement of matter, it's a fundamental reconfiguration of the particles themselves. The star, in essence, becomes a giant nucleus made almost entirely of neutrons. This transformation is astonishing. Neutrons are neutral particles, lacking electrical charge, which means they can pack together far more closely than protons or electrons ever could. The result is matter so dense that the human imagination struggles to comprehend it. Imagine taking the Sun, an object over a million times the size of Earth, and squeezing it into a sphere barely 20 kilometers across. That is what a neutron star is, a celestial body so compact that a single teaspoon of its material would weigh billions of tons. Yet the story does not stop at density alone. Neutron stars also possess some of the most extreme physical properties in the universe. They spin at breathtaking speeds, sometimes hundreds of times per second, turning into cosmic lighthouses known as pulsars, which beam radiation like a strobe light sweeping across the galaxy. Their magnetic fields are trillions of times stronger than Earth's, powerful enough to distort atomic structures and rip electrons away from atoms with ease. These magnetic fields give rise to magnetars, neutron stars whose violent magnetic eruptions can outshine entire galaxies for brief moments. What's truly remarkable is that these objects, as alien as they sound, are not entirely hypothetical. We have observed neutron stars through their pulsations, their emissions, and their interactions with surrounding matter. We have even detected gravitational waves from neutron star collisions, confirming their existence not just through light but through ripples in space-time itself. Neutron stars are the proof that nature can take ordinary matter, atoms, nuclei, electrons, protons, and compress it into something so radical that it becomes unrecognizable. Inside a neutron star, there is no room for the familiar structure of atoms. Electrons no longer orbit nuclei. Instead, matter is stripped to its core identity. The immense pressure forces electrons into protons, and the result is a mass of neutrons pressed so tightly together that they form what scientists call neutron-degenerate matter. This is a state of matter unlike anything we encounter on Earth, a state where quantum mechanics plays as much a role in holding up the star as gravity does in trying to crush it further. But the question that haunts astrophysicists is this: does the collapse stop there? We know that neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being packed too closely, is what keeps the neutron star from collapsing further. But could there be situations where even this remarkable force fails? Could the neutrons themselves break down under pressures beyond comprehension? If that happens, the star would no longer be made of neutrons at all. Instead, it would reveal what lies deeper: the quarks, the fundamental particles that make up neutrons and protons alike. Neutron stars, then, are not just an endpoint in stellar evolution. They may be the gateway to something even stranger. They represent the boundary between what we can observe and what we can only hypothesize. They are the halfway house between ordinary matter and the theoretical quark matter that could redefine our understanding of the universe. And so, when we think of neutron stars, we should not see them as the final word in stellar death, but rather as a critical clue, a cosmic stepping stone. They remind us that the universe is capable of creating environments where matter is pushed to its ultimate limits. And just beyond that threshold lies the possibility of something even more exotic: quark stars. To understand that possibility, we must now ask the question: what happens when neutrons themselves are forced to break apart? When we arrive at the threshold of neutron stars, we are already dealing with matter compressed beyond the limits of imagination. A neutron star represents a triumph of physics. Gravity pulls with such ferocity that atoms cannot survive, protons and electrons fuse into neutrons, and the result is an object so dense that it defies our earthly intuition. But even this may not be the end of the story. If the collapse continues and the pressures grow even more overwhelming, a new and astonishing possibility emerges. The neutrons themselves may no longer be able to endure. They could break apart, dissolving into their most fundamental building blocks, quarks. To appreciate how extraordinary this idea is, think about what a neutron really is. It's not indivisible. Neutrons, along with protons, belong to a family of particles called hadrons, which are made of even smaller particles bound together by the strong nuclear force. Each neutron is composed of 3 quarks, 2 down quarks and 1 up quark. These quarks are locked inside the neutron, held together by gluons, the force carriers of the strong interaction. Under normal conditions, quarks are permanently confined within protons and neutrons. They never roam freely. But what if the conditions are no longer normal? Inside a collapsing star, the pressures and densities are so extreme that the ordinary rules begin to crack. Just as atoms cannot survive inside a neutron star, neutrons themselves may not survive under conditions beyond what even neutron degeneracy pressure can resist. In such an environment, the neutrons are crushed so tightly together that they effectively melt. Their quarks are released from their confinement, no longer bound into neat packages of 3. Instead, the star becomes filled with a fluid-like soup of quarks and gluons. This process is sometimes called deconfinement. It's the breakdown of the barriers that normally keep quarks trapped inside particles. It's like dissolving a brick wall into its individual bricks, except these bricks are the smallest, indivisible particles that we know of. What remains is a new kind of matter, far stranger and denser than even neutron matter: quark matter. The concept of quark matter is not mere speculation born out of science fiction. In fact, we already know that under certain conditions, quarks can be freed. In high-energy particle accelerators on Earth, such as those at CERN, physicists have been able to briefly create a state of matter known as the quark-gluon plasma, a hot soup of quarks and gluons thought to resemble the universe as it existed microseconds after the Big Bang. However, those laboratory conditions are fleeting, lasting only fractions of a second, and existing at temperatures trillions of degrees hot. What we're speaking of in stars is something far more stable, colder, and lasting, a star whose very substance is made of quarks. Imagine the drama of this transition. The neutron star, already compacted into an object no larger than a city but heavier than the Sun, continues to collapse. The neutrons, already the last line of defense against gravity, begin to dissolve. Instead of a star made of neutrons jammed side by side, you now have an ocean of quark matter, a star where the very particles that form the scaffolding of reality have been unshackled. What makes this idea both haunting and fascinating is that we have no clear sense of how such matter behaves on cosmic scales. Quarks are governed by quantum chromodynamics, a theory that is still full of mysteries when it comes to extreme pressures and densities. What we do know is that the physics would be unlike anything in a neutron star or black hole. A quark star would represent a new category of stellar remnant, occupying a narrow but profound space between what is known and what is hidden. This is why neutron stars are so important. They are the doorway to this possibility. They show us what happens when matter is stripped of its atoms and forced into neutrons. But beyond that door, under conditions we can only imagine, lies the world of quark matter. If nature permits it, if the collapse stops just before the point of no return into a black hole, then the universe could be harboring objects where neutrons themselves no longer exist as neutrons, but as a churning sea of quarks. So the question becomes, what exactly are quarks, these elemental building blocks of neutrons and protons? If quark stars exist, understanding quarks themselves becomes essential, because such a star would not be made of ordinary matter at all. It would be made of the purest, most fundamental substance we know. And so, to continue this journey, we must step down one more level, from neutrons to the quarks themselves. Quarks are the very foundation stones of the universe's architecture. If you peel away the layers of matter, you find molecules. Strip those molecules down further, you get atoms. Break those atoms apart, and you uncover protons and neutrons at their core. And if you ask, what lies inside those protons and neutrons? The answer is quarks. They are not just smaller pieces of matter, they are fundamental particles, meaning as far as we know, they cannot be broken down into anything else. They are the ultimate pixels from which much of the visible universe is drawn. There are 6 known types of quarks, often called flavors: up, down, strange, charm, top, and bottom. In the everyday matter that makes up stars, planets, and people, only 2 of these, up and down quarks, play the main roles. A proton is composed of 2 up quarks and 1 down quark. A neutron is the opposite arrangement, 2 down quarks and 1 up quark. The other 4 quark flavors, while real, exist only in extreme conditions such as high-energy particle collisions or in the fleeting moments after the Big Bang. What makes quarks truly fascinating is how they are held together. Quarks are bound by the strong nuclear force, the most powerful fundamental force in nature. This force is carried by particles called gluons, and it is so strong that quarks can never normally exist alone. The more you try to pull quarks apart, the stronger the force becomes, like a rubber band stretched tighter the farther it's pulled. At some point, instead of isolating one quark, the energy you put in simply creates new quark pairs. This phenomenon, known as color confinement, is why free quarks have never been observed in isolation. Yet the idea of quark stars pushes this principle to its breaking point. If matter is compressed so intensely that protons and neutrons dissolve, quarks may no longer be confined to triplets inside individual particles. Instead, they could exist in a vast collective state, a sea of quark matter. Imagine an entire star where the rules of matter as we know them are rewritten, and the universe's fundamental building blocks roam freely in bulk. That is the essence of the quark star hypothesis. This prospect raises strange and compelling questions. What would such matter feel like? What properties would it have? Could it be stable, or would it try to reassemble into neutrons and protons? Some theories suggest that under the crushing pressures of a quark star, quarks could combine in unusual ways, forming not just the familiar up and down varieties, but also strange quarks. This would create what physicists call strange matter, an exotic substance that might be even more stable than ordinary matter itself. The leap from neutrons to quarks is not just a step down in size, it is a leap into a new regime of physics. While neutron stars challenge our understanding of quantum mechanics and relativity working together, quark stars would force us to grapple with the mysteries of quantum chromodynamics on a cosmic scale. If real, they would not just be stars, they would be vast laboratories made of quark matter, allowing us to glimpse what the universe itself might have looked like in its first fractions of a second. Quarks, then, are not just the stuff of neutrons and protons. They are a reminder that beneath the familiar lies a hidden structure, and beneath that structure lies the possibility of entire new forms of matter. A quark star would be the ultimate expression of this possibility, a celestial body not made of atoms, or even neutrons, but of the pure quark fabric from which those things emerge. And this leads us directly to the next step in our journey, the quark star hypothesis itself. How do astrophysicists envision such an object forming? How would it exist? And what would separate it from its neutron star cousins? To answer that, we must step fully into the strange world of stars made entirely of quarks. The quark star hypothesis is one of the most daring ideas in modern astrophysics. It suggests that the universe might harbor a type of star even more exotic than neutron stars, yet not quite the same as black holes. These hypothetical objects, called quark stars, would be born when the crushing weight of gravity forces matter beyond the neutron stage. Instead of a star made of neutrons pressed together like a cosmic brick wall, a quark star would be a liquid sea of free quark matter, a star where neutrons themselves have dissolved into their constituent parts. To picture this, it helps to revisit the evolutionary ladder of stellar remnants. A white dwarf is supported by electron degeneracy pressure, the quantum mechanical resistance of electrons against being packed too tightly. A neutron star is supported by neutron degeneracy pressure, the same principle, but acting on neutrons. Each step is stranger, denser, and more extreme than the last. But what happens if gravity squeezes so hard that even neutrons cannot hold their ground? The neutrons break apart, and the star becomes a quark star. This is the central idea of the hypothesis. A quark star is a collapsed star whose core is made not of atoms, nor neutrons, but of quark matter. In this state, the strong force that normally confines quarks inside protons and neutrons yields to the overwhelming density, allowing quarks to roam freely in a new phase of matter. Instead of discrete neutrons stacked against one another, the star's core becomes a continuous soup of quarks and gluons, possibly forming structures and behaviors unlike anything we've seen in ordinary matter. One of the most remarkable features of this hypothesis is how delicately balanced such a star would be. A quark star is thought to form when a collapsing neutron star does not have enough mass to become a black hole, but just enough to push its matter past the neutron degeneracy threshold. That means quark stars could exist in a very narrow window between neutron stars and black holes. Too light, and the star remains a neutron star. Too heavy, and it collapses into a black hole. But in that small, precarious middle ground, a quark star might emerge. If they do exist, quark stars would likely be smaller than neutron stars, since quark matter can be packed even more tightly. A typical quark star might be only 10 kilometers across, about the size of a large city, but contain more mass than our Sun. Imagine an entire star crushed into something that could sit comfortably within the sprawl of Manhattan, yet so dense that a spoonful of its substance would outweigh mountains. Astrophysicists sometimes describe quark stars as the last stop before the abyss. They are cosmic laboratories of extreme physics, frozen snapshots of matter at its most fundamental level, sitting on the razor's edge of collapse. While they would outwardly resemble neutron stars, hot, compact, and with incredibly strong magnetic fields, their internal structure would be fundamentally different. Instead of a rigid crust of neutrons, they would have a core of quark matter, perhaps even extending all the way to their surface. The idea of quark stars is more than an academic curiosity. If confirmed, their existence would prove that matter can exist in phases beyond what we encounter in ordinary stars or even neutron stars. They would demonstrate that the universe has found a way to create stable, large-scale structures out of quark matter, something scientists have only glimpsed briefly in high-energy collisions on Earth. It would be as if the cosmos itself were showing us a deeper layer of its construction manual. But what makes quark stars even more intriguing is the possibility that quark matter might not just involve the familiar up and down quarks. Under such pressures, strange quarks could also appear, creating what is known as strange matter, a form of quark matter that may be more stable than anything we know. If true, quark stars would not just be exotic, they might represent the most stable form of matter in the universe. Thus, the quark star hypothesis is not merely about a new type of star. It is about uncovering an entirely new chapter in the story of matter itself. If nature does allow these stars to exist, then somewhere in the universe, far beyond our reach but still within our telescope's grasp, there may be stars shining faintly in the darkness. Stars that are not made of atoms or neutrons, but of the very essence of quarks. And this naturally brings us to one of the most tantalizing ideas tied to quark stars: the possibility that quark matter may come in an even stranger form, involving quarks beyond the usual up and down. Could the universe be sprinkled with stars made of strange matter, a substance that challenges the very idea of what is stable and what is not? The concept of quark matter naturally leads us into one of the most fascinating and counterintuitive ideas in modern astrophysics: strange matter. Quark stars, if they exist, may not be composed solely of the familiar up and down quarks found in ordinary neutrons and protons. Under the extreme densities and pressures found inside these hypothetical stars, the energy conditions could allow another quark flavor, the strange quark, to appear, fundamentally altering the nature of the matter within. To understand why this is so remarkable, it helps to recall that quarks come in 6 flavors: up, down, strange, charm, top, and bottom. Everyday matter only uses up and down quarks. Neutron stars push matter to incredible densities, packing neutrons so tightly that they almost touch. But when density and pressure go even further, as theorized for quark stars, the energy per quark becomes high enough that producing strange quarks is energetically favorable. Essentially, the matter decides to convert some of its up and down quarks into strange quarks because doing so reduces the overall energy of the system. When a significant number of quarks in a star include strange quarks, the resulting substance is called strange matter. Unlike normal quark matter, which consists only of up and down quarks, strange matter contains a mixture of up, down, and strange quarks in roughly equal proportions. The presence of strange quarks changes the physical properties of the star dramatically. It makes the matter more stable at extremely high densities, because the addition of the strange quark flavor allows the quarks to arrange themselves in a lower energy configuration. In simple terms, strange matter could be more stable than neutron matter, possibly even more stable than ordinary atomic matter under certain conditions. The implications of strange matter are both thrilling and unsettling. If strange matter is indeed the most stable form of matter, a single droplet, sometimes called a strangelet, could, in theory, trigger the conversion of ordinary matter into strange matter under the right circumstances. This hypothetical chain reaction has captured the imaginations of physicists and science fiction writers alike. While such a scenario is extremely unlikely in nature due to energy barriers and cosmic conditions, it highlights just how alien and powerful strange matter could be. Inside a strange quark star, the bulk of the star could be composed entirely of strange matter. This changes the star structure compared to a neutron star. While neutron stars are supported against collapse by neutron degeneracy pressure, strange matter may support the star through a combination of quark degeneracy pressure and strong interactions between quarks. As a result, strange quark stars could potentially be smaller, denser, and more compact than neutron stars of similar mass. A star that weighs as much as the Sun could be compressed into a sphere just 10 kilometers across, yet the quark matter inside could remain stable, even under pressures that would otherwise create a black hole. The potential stability of strange matter also has cosmic implications. If strange matter is more stable than nuclear matter, then it might have been present in the early universe, influencing the formation of stars and galaxies in subtle ways. Some theorists speculate that strange quark nuggets might even drift through space as relics of the Big Bang, undetectable to us except through rare interactions. In this sense, strange matter could be a hidden but pervasive ingredient of the cosmos, existing silently in forms we are only beginning to theorize about. Moreover, strange matter may help explain some astrophysical mysteries. Certain pulsars and compact objects exhibit unusual behavior, like rapid cooling or odd rotation patterns, that are difficult to reconcile with standard neutron star models. The presence of strange quark matter could account for these anomalies, providing a tantalizing hint that quark matter and strange matter may indeed be more than theoretical constructs. Ultimately, strange matter pushes the boundaries of our understanding of matter itself. It represents a form of matter that is both fundamentally exotic and potentially extremely stable, challenging our assumptions about what matter can be. If quark stars contain strange matter, then the universe is hosting objects that are not just extraordinary in density or mass, but extraordinary in their very essence, objects whose internal structure operates according to principles that exist nowhere else we know, either in Earth-based laboratories or in ordinary stars. Thus, quark matter and strange matter are not merely extensions of neutron star physics. They represent a wholly new regime of reality. They hint at an extreme, hidden world of matter where the universe itself is distilled down to its most fundamental components, reshaped in ways that defy everyday intuition. From here, we can start to make sense of how dense these objects could become, and how their extreme compactness compares even to neutron stars and black holes. The extreme nature of quark stars becomes especially striking when we consider their density. which places them among the densest objects in the universe, rivaling black holes in their ability to compress matter but stopping short of collapsing completely. To grasp the magnitude of this density, it helps to compare quark stars with neutron stars and black holes using analogies that bring the incomprehensible scale down to something we can imagine. A neutron star is already an almost inconceivably dense object. Its mass, often between 1.4 and 2 times that of the Sun, is packed into a sphere with a radius of just 10 to 20 kilometers. To put that into perspective, a teaspoon of neutron star matter would weigh roughly 1 billion tons, equivalent to the combined weight of hundreds of Great Pyramids of Giza. If you could somehow lift a cube of neutron star matter the size of a soda can, its weight would be comparable to a mountain. The reason for this incredible density is that neutrons, which are normally packed loosely inside atomic nuclei, are crushed together so tightly that they form a near-perfect neutron-degenerate fluid. Quark stars take this compression one step further. If a neutron star's neutrons melt into quarks under extreme pressure, the resulting quark matter can be packed even more densely. While the precise density depends on the star's mass and the behavior of quark matter under such extreme conditions, estimates suggest that quark stars could be 30 to 50% denser than neutron stars, or even more. A teaspoon of quark star matter could weigh tens of billions of tons, possibly approaching the theoretical densities at which matter begins to resemble the interior of a black hole. Black holes, by contrast, represent a fundamentally different case. Their defining feature is the event horizon, beyond which not even light can escape. Within that horizon, matter collapses toward a singularity, a point of effectively infinite density in classical general relativity. Unlike neutron stars or quark stars, whose density is extreme but finite, black holes defy direct physical intuition. A black hole of the Sun's mass, if it could be compressed into a single point, would have a density vastly greater than anything else in the universe, but this is a theoretical extrapolation. In contrast, quark stars occupy a middle ground. Their density approaches, but does not reach, the point of forming a singularity. To illustrate this further, consider another analogy. If the Sun were converted into a neutron star, it could fit into a city-sized sphere, weighing as densely as an entire solar mass in a space only kilometers across. If it were instead converted into a quark star, that same mass could be compressed into an even smaller volume, maybe a sphere barely a few kilometers across, without collapsing into a black hole. Meanwhile, a black hole of equivalent mass has no meaningful volume in classical physics. It is defined by the curvature of spacetime around it rather than the matter it contains. This density ladder is important in understanding why quark stars are theoretically possible. They represent a bridge between neutron stars and black holes, matter compressed beyond the neutron stage but still able to resist full gravitational collapse. The strong nuclear force and quark degeneracy pressure combine to halt collapse, creating an object that is extraordinarily compact yet stable. In some ways, a quark star could be thought of as the universe's ultimate demonstration of matter resisting obliteration. Matter pressed almost to its absolute limit, but still not fully lost to gravity. Another striking point is that the surface of a quark star would be extremely sharp in density contrast compared to its surroundings. Whereas neutron stars may have a thin crust of neutrons or nuclei above a dense core, quark stars could have a core that extends directly to the surface, meaning that the jump in density from space to the star's surface could be truly astonishing. Touching the surface, hypothetically, would be like plunging your hand through the vacuum of space and immediately encountering material heavier than a mountain compressed into a cubic centimeter. Understanding the density comparison also illuminates why quark stars are so difficult to observe. Externally, their gravitational pull might be similar to a neutron star of equivalent mass. Their size is smaller, their density higher, but their light emissions and other external markers could resemble those of neutron stars, making them extremely subtle to detect. Only under precise measurements, such as cooling rates, pulsation patterns, or gravitational wave signatures, might we detect the differences between an extraordinarily dense neutron star and a quark star. Thus, the density comparison does more than highlight the sheer extremity of quark stars. It places them in a conceptual spectrum of cosmic extremes. On one end, neutron stars compress ordinary nuclear matter into a city-sized sphere. Quark stars push beyond that, concentrating matter even further into almost unimaginable densities, a bridge between matter and the event horizon of a black hole. On the other end, black holes represent the final surrender of matter to gravity, collapsing entirely into space-time curvature. Quark stars, if they exist, occupy that precarious, almost mystical middle ground, where matter itself is tested to the absolute limits without disappearing entirely. This extreme density naturally leads to questions about the size of these stars and how something so massive could fit into a volume so small, which is the next step in understanding the unique nature of quark stars. The remarkable density of quark stars directly dictates their size, creating objects that are astoundingly compact yet enormously massive. Whereas our Sun stretches across roughly 1.4 million kilometers in diameter, a quark star of similar mass could be confined to a sphere only a few kilometers across, roughly the size of a small city. To grasp this, we need to think about how matter behaves under extreme compression and why quark matter allows such extraordinary compaction. In ordinary stars, like our Sun, thermal pressure from nuclear fusion counteracts gravity. The Sun maintains its vast size because the outward force of fusion balances the inward pull of gravity. Neutron stars, which no longer sustain fusion, rely instead on neutron degeneracy pressure to resist further collapse. Degeneracy pressure is a quantum mechanical phenomenon. Particles resist being squeezed into the same state, which in neutron stars manifests as a rigid opposition to further compression. This is why neutron stars, despite packing more mass than the Sun, only measure 10 to 20 kilometers across. Quark stars take this compression further. Once neutrons dissolve into quark matter, the constituents of the star, up, down, and potentially strange quarks, are packed in an even denser configuration. Quarks obey quark degeneracy pressure and are bound together by the strong nuclear force, allowing matter to be compressed beyond the limits of neutron degeneracy. The result is a star smaller than a typical neutron star, possibly only 8 to 12 kilometers in diameter for a star weighing about 1 to 2 solar masses. To appreciate this visually, imagine compressing the entire Sun into a sphere smaller than Manhattan. The volume shrinks dramatically, but the mass remains the same. This means the gravitational pull at the surface is enormously strong, comparable to, or even exceeding, that of a neutron star. If a person could stand on the surface, hypothetically ignoring tidal forces, crushing gravity, and extreme radiation, they would weigh billions of tons. Every centimeter squared of the quark star's surface would bear a force greater than a mountain range. Interestingly, the small size of quark stars has implications for their observational properties. A star this compact produces extremely high surface gravity, which influences the light escaping from it. Photons emitted near the surface are redshifted by the immense gravitational field, stretching their wavelengths. This redshift could be one of the subtle observational signatures that differentiate a quark star from a neutron star. Additionally, the smaller radius means that quark stars could spin faster than neutron stars without tearing themselves apart, potentially producing extremely rapid pulsations that could be detectable with sensitive instruments. The size also affects the thermal and magnetic properties of the star. Because quark stars are so compact, heat is distributed over much smaller volume. This can lead to unusual cooling rates, as the heat escapes more efficiently through the thin crust or even a bare quark surface. Similarly, magnetic fields could be extraordinarily strong due to the small radius concentrating magnetic flux, creating surface fields trillions of times stronger than Earth's. These extreme conditions make quark stars laboratories of physics that cannot be reproduced anywhere else in the universe. Despite their tiny size, quark stars are incredibly massive, often 1.5 to 2 solar masses or more. In comparison, a neutron star of similar mass is slightly larger, making quark stars denser by tens of percent. This tight packing is a consequence of quark matter's properties, which allow the star to resist collapse more efficiently at extremely high densities. In other words, the star is holding itself together in a state that is denser and smaller than anything observed in ordinary neutron stars. This combination of tiny size and enormous mass places quark stars in a unique position in the cosmic landscape. They are more compact than neutron stars, yet not collapsed into a black hole. They represent a fine balance. Gravity presses inward, and the exotic pressures of quark matter push outward, creating a stable but incredibly dense object. This delicate equilibrium is what makes them so fascinating to theorists. If observed, quark stars would be among the most extreme objects in the universe in terms of both density and mass-to-size ratio. Understanding this balance also raises questions about how quark stars form in the first place. How does a neutron star transition into a quark star without becoming a black hole? What mechanisms allow matter to dissolve into quarks and then stabilize into a compact star? These questions lead us naturally into the theoretical formation scenarios, which attempt to explain the life and birth of these extraordinary objects. The formation of a quark star is one of the most intriguing and speculative topics in astrophysics because it requires the universe to operate at the limits of what is physically possible. It begins with a neutron star, the already extreme product of stellar collapse. But under certain circumstances, the neutron star can be pushed even further, creating conditions where quarks themselves break free and form a new state of matter. Understanding this process requires a careful look at the delicate balance between gravity, which relentlessly crushes matter inward, and the degeneracy pressures and strong nuclear forces that resist this compression. A neutron star forms from the catastrophic collapse of a massive star following a supernova explosion. Normally, neutron degeneracy pressure halts the collapse, creating a dense, city-sized object composed mostly of neutrons. But if the neutron star accumulates additional mass, through accretion from a companion star, merges with another neutron star, or internal processes, the balance can tip. When the core mass of a neutron star approaches the Tolman-Oppenheimer-Volkoff limit, the maximum mass a neutron star can sustain against gravitational collapse, typically estimated around 2 to 3 solar masses, the internal pressure may no longer be sufficient to prevent further compression. At this tipping point, the extreme density and pressure could trigger the dissolution of neutrons into quarks. In other words, the neutrons melt, forming quark matter at the star's core. If the mass is just below the threshold for black hole formation, the quark matter can stabilize the star, preventing complete collapse. The result is a quark star, a stable object more compact and denser than a neutron star, yet not a black hole. One proposed pathway to forming a quark star is through neutron star mergers. When two neutron stars spiral into each other and collide, the combined mass and energy can briefly create conditions exceeding neutron degeneracy limits. During the merger, some regions may exceed the density threshold required for quark deconfinement. After the violent interaction, if the merged object's mass is within the right range, it may settle into a quark star rather than collapsing entirely into a black hole. These merger events are already being observed indirectly through gravitational wave detectors, such as LIGO and Virgo, which record ripples in space-time from such catastrophic collisions. Some of these signals may one day reveal the formation of quark stars. Another theoretical scenario involves massive accretion onto an existing neutron star. In binary systems, a neutron star can siphon matter from a companion star. As this mass accumulates, the central density rises. If the pressure exceeds what neutrons can sustain, a core of quark matter may form. This quark core could expand gradually, converting the entire star into a quark star if the mass and density conditions remain favorable. The fascinating thing about quark star formation is that it represents a narrow window of possibility. If the collapsing mass is too small, the star remains a neutron star. If the mass is too large, it collapses fully into a black hole. Quark stars occupy the precarious middle ground, balancing on the edge of gravitational destruction while holding themselves together through exotic pressures derived from quark matter. It's a cosmic tightrope act that could be fleeting, difficult to produce, and even harder to observe. The conversion process itself, from neutron star to quark star, could release enormous amounts of energy. As neutrons dissolve into quarks, the star's core density increases, potentially generating a shockwave that propagates outward. Some theorists speculate that such a process could be responsible for certain types of gamma-ray bursts or unusual X-ray emissions observed from compact stellar remnants. The conversion might be gradual, or it could be catastrophic, but either way, it would mark the birth of an entirely new form of celestial object. It's important to note that this entire process is theoretical. No quark star has been definitively observed yet. What we do know is that the universe is capable of creating extreme densities, and quark matter has been briefly created in particle accelerators. The leap from laboratory quark-gluon plasma to a stable, massive quark star is immense, but physically plausible according to quantum chromodynamics and models of high-density matter. In essence, the formation of a quark star is a story of extreme thresholds. The universe pushes a neutron star to its absolute limits, through mergers, accretion, or internal instabilities, and if the conditions are perfect, a new state of matter emerges, frozen in a delicate equilibrium. Gravity has been tamed just enough by the exotic pressures of quark matter, creating a star that is simultaneously heavier than the Sun, smaller than a city, and more mysterious than any ordinary stellar remnant. From here, The question naturally arises: if such a star exists, how could we detect it? What would make a quark star observable? And why have we not confirmed their existence yet? These questions lead us into the observational challenges surrounding quark stars, a topic that is crucial to connecting theory with reality. Observing quark stars is one of the greatest challenges in modern astrophysics, precisely because they are so similar in appearance to neutron stars. From afar, a quark star might look almost identical to a neutron star, a compact, dense, spinning object emitting X-rays, gamma rays, and sometimes radio waves. Their extreme gravity bends light, their magnetic fields can produce pulsar-like emissions, and their surface temperatures can generate thermal radiation, all features we already associate with neutron stars. This similarity makes distinguishing a quark star from a neutron star extraordinarily difficult. The first difficulty arises from size and mass measurements. Neutron stars and quark stars can have overlapping mass ranges, typically 1.4 to 2 solar masses, and similar radii, with quark stars potentially being slightly smaller. From Earth, measuring these properties directly is a monumental task. Astronomers rely on indirect methods such as X-ray spectroscopy, gravitational lensing, or timing observations of pulsars. Even tiny uncertainties in these measurements can make the difference between labeling an object a neutron star or suspecting it might be a quark star. Another challenge is emission similarity. Neutron stars emit radiation across the electromagnetic spectrum due to residual heat, magnetic activity, or accretion from companion stars. Quark stars, while structurally different inside, would also emit X-rays and gamma rays through these same mechanisms. A distant quark star could therefore masquerade as an ordinary neutron star, with no immediately obvious signature of its exotic interior. The thermal and magnetic properties might differ slightly, but detecting these subtle differences requires extremely precise instruments and favorable conditions. Then there is the issue of gravitational effects. Both neutron stars and quark stars warp spacetime dramatically. Their immense gravity can bend light, influence orbital motion of companion stars, and create gravitational waves if in a binary system. While quark stars may be slightly more compact, the difference in gravitational influence may be too subtle for current detection methods, especially across the vast distances of space. One of the most intriguing observational challenges is the surface composition. Neutron stars have a crust of neutron-rich nuclei above a core of neutrons. Quark stars might lack a crust entirely, exposing bare quark matter at their surface, or perhaps a very thin crust forms over the quark core. However, the difference in emissions between a thin nuclear crust and a bare quark surface might be minuscule or hidden beneath intervening plasma and radiation, making it extremely difficult to detect even with powerful telescopes. Adding to the difficulty, quark stars may mimic the behavior of neutron stars in pulsar timing and rotation. Pulsars, spinning neutron stars emitting regular beams of radiation, can be used to study mass, radius, and moment of inertia. Quark stars, being smaller and denser, could potentially spin faster, but without a population of extremely fast pulsars with unusual properties, it is nearly impossible to use rotation alone to identify them. Any observed anomaly could also be explained by variations in neutron star structure, magnetic fields, or accretion effects. The rarity of quark stars further compounds the problem. If they only form in a narrow mass range or under specific conditions, such as a neutron star approaching the Tolman-Oppenheimer-Volkoff limit or during rare mergers, they may be exceptionally scarce. Detecting one among billions of neutron stars is like trying to identify a single snowflake in a blizzard. Even if they are out there, we might simply be looking in the wrong way, or at the wrong objects, to spot them. Finally, cosmic distances and interstellar interference complicate observations. X-rays and gamma rays can be absorbed or scattered by interstellar dust, while gravitational effects diminish with distance. By the time signals reach Earth, they are faint and subtle, demanding instruments of extraordinary sensitivity. Even then, any anomalous signal must be carefully distinguished from more mundane explanations, such as magnetic field variations, accretion phenomena, or binary interactions. In short, quark stars may be hiding in plain sight. They could be masquerading as ordinary neutron stars in X-ray surveys, pulsar catalogs, or even gravitational wave detections. The differences are subtle: slightly smaller radius, slightly faster spin, unusual cooling, or exotic emission patterns. But teasing out these signals requires precision, patience, and often a bit of luck. This is why, despite decades of observations, no quark star has been definitively confirmed, and they remain one of the most tantalizing mysteries in astrophysics. However, even though identifying them is difficult, theorists have proposed potential signatures that might reveal their presence. Certain behaviors, cooling rates, unusual X-ray emissions, or sudden bursts of energy could hint at a quark star rather than a neutron star. These possibilities give astronomers hope that, with the right tools, quark stars may eventually be distinguished from their more familiar cousins. Understanding these potential observational signatures is crucial, because they offer the best chance of moving quark stars from theory into reality. If we can identify even one quark star, it would confirm the existence of a completely new state of matter in the universe, with profound implications for physics, cosmology, and our understanding of the extremes of matter. Detecting quark stars is a monumental challenge, but theorists have proposed several potential signatures that could distinguish them from ordinary neutron stars. These signals hinge on the unique physical properties of quark matter and the extreme conditions inside such stars. While no quark star has been definitively confirmed, these theoretical markers provide astronomers with clues to guide their searches. One of the most promising potential indicators is unusual cooling behavior. Neutron stars cool primarily by emitting neutrinos from their dense interiors and photons from their surfaces. This cooling process is relatively well understood and follows a predictable curve over thousands to millions of years. Quark stars, however, could cool in markedly different ways due to the presence of quark matter. In particular, quark matter allows rapid neutrino emission through processes like the direct Erka process involving quark decay. This would cause a quark star to lose heat much faster than a neutron star of similar mass and age. Observationally, this could manifest as a compact star that is unexpectedly cold for its estimated age, deviating from standard neutron star cooling models. Detecting such anomalous thermal signatures would require sensitive X-ray and ultraviolet observations to measure surface temperatures with high precision. Another potential signature lies in X-ray emissions. Neutron stars emit X-rays due to residual heat, magnetic activity, or accretion from a companion. Quark stars, with their denser cores and possibly bare quark surfaces, might exhibit distinct X-ray spectra compared to neutron stars. For instance, the surface of a quark star could emit harder X-rays or display unusual line features due to interactions between quark matter and surrounding plasma. In some models, quark stars could have thermal emission patterns that differ from the blackbody spectra of neutron stars, particularly if the quark matter interacts differently with magnetic fields or if the star has a minimal or no crust. Detecting such anomalous X-ray emissions would require high-resolution spectroscopy from instruments like NISA, Neutron Star Interior Composition Explorer, or future space-based X-ray observatories. Sudden bursts of energy, particularly in the gamma-ray spectrum, may provide another way to identify quark stars. Some theorists suggest that transitions within the quark matter itself, such as rearrangements between up, down, and strange quarks, could release enormous amounts of energy almost instantaneously. These events might resemble short gamma-ray bursts, GRBs, which are already observed in the universe and typically associated with neutron star mergers. A quark star could produce similar bursts during its formation or if a neutron star converts into a quark star. Such bursts would likely be brief but incredibly energetic, potentially offering a transient signal that distinguishes quark stars from ordinary compact objects. Rotation and pulsation patterns provide another potential diagnostic. Quark stars, being smaller and denser than neutron stars, could theoretically spin faster without breaking apart. A millisecond pulsar exhibiting unusually high rotational stability, or one with unexpected glitches or timing irregularities, could hint at the presence of a quark core. Observations of pulsar timing irregularities, sudden changes in rotational period, could provide indirect evidence for a quark star, especially if these deviations are inconsistent with neutron star models. Additionally, gravitational waves offer a promising avenue. Quark stars in binary systems could merge or interact in ways slightly different from neutron stars due to their higher compactness. The gravitational wave signals from such events could contain subtle clues in the waveform. Differences in tidal deformability, merger dynamics, or post-merger oscillations might reveal a quark matter interior. Advanced gravitational wave detectors, like LIGO, Virgo, and future space-based observatories, may be able to discern these differences in high-precision measurements. In some cases, Strange quark matter nuggets, if ejected from a quark star, could provide additional observational evidence. These hypothetical droplets of strange matter, called strangelets, would be incredibly dense and stable, and might interact in unusual ways if they collided with ordinary matter. While direct detection is extremely unlikely, cosmic ray detectors or experiments designed to search for ultradense particles could, in principle, detect them, offering indirect evidence for quark star interiors. Combining these potential signatures, rapid cooling, unusual X-ray spectra, sudden gamma-ray bursts, rotational anomalies, and gravitational wave observations, provides a multi-pronged approach for identifying quark stars. No single observation is likely to be conclusive, given how similar quark stars may appear to neutron stars. Instead, researchers would need corroborating evidence across multiple channels to make a convincing case. Ultimately, the search for quark stars is a combination of theoretical prediction and cutting-edge observation. The universe may already be sending us signals in X-rays, gamma rays, or gravitational waves that hint at these exotic objects. The challenge is separating the subtle signs of quark matter from the background noise of ordinary neutron stars, black holes, and other astrophysical phenomena. If successful, such observations would not only confirm the existence of quark stars but also reveal a new state of matter, one that exists nowhere else in the known universe. While quark stars remain hypothetical, astronomers have identified several candidate objects in the universe that exhibit unusual properties, sparking speculation that they might be more than ordinary neutron stars. These candidates provide tantalizing clues, though none has yet been definitively confirmed as a quark star. Examining these objects helps us understand both the challenges and possibilities in identifying quark stars. One of the most famous candidates is RxJ 1856.5-3754, an isolated neutron star-like object located roughly 400 light-years from Earth in the constellation Corona Australis. RxJ 1856.5-3754 has intrigued astronomers for decades because of its small radius and thermal properties. Observations suggest that its radius is significantly smaller than what would be expected for a neutron star of its mass. Additionally, its surface temperature and X-ray spectrum do not entirely match standard neutron star models. These peculiarities have led some theorists to propose that RxJ 1856.5-3754 could be a quark star, with a core or perhaps an entire structure composed of quark matter. Its compactness, coupled with thermal emission anomalies, makes it one of the strongest candidates for an exotic compact object. Another intriguing set of candidates comes from pulsars exhibiting unusual rotational behavior. Pulsars are rapidly rotating neutron stars emitting beams of electromagnetic radiation, but some pulsars display timing irregularities, glitches, or unexpectedly fast spin rates that challenge conventional models. For example, certain millisecond pulsars appear to rotate faster than expected for neutron stars of their inferred mass and radius. This could indicate a smaller, denser object, consistent with a quark star. The higher density of quark matter allows the star to sustain faster rotation without breaking apart, which might explain these extreme pulsation properties. Some binary systems also provide hints. Compact objects in low-mass X-ray binaries sometimes exhibit characteristics inconsistent with neutron star models. For instance, certain X-ray bursts occur with unusual energy profiles or cooling times that suggest a more compact and denser interior than standard neutron star theory predicts. These bursts could potentially originate from quark stars, whose internal physics and heat transport differ due to the presence of quark matter or strange quark matter. Another notable candidate is the pulsar PSR-J 1614-2230, one of the most massive neutron star-like objects ever measured, with a mass of around 2 solar masses. While technically consistent with a heavy neutron star, some models suggest that a star of this mass could exceed the stability limit of ordinary neutron matter, potentially implying the presence of a quark core. Similarly, PSR-J 0348+0432, another massive pulsar, has sparked discussions about the possibility of quark matter at its core due to its extreme mass combined with observed radius constraints. Gamma-ray bursts and X-ray transients have also been proposed as indirect indicators. Some short gamma-ray bursts, thought to originate from neutron star mergers, display afterglow and cooling patterns inconsistent with standard neutron star physics. In these cases, theorists have speculated that the remnant could be a quark star formed during the merger, temporarily resisting collapse into a black hole while exhibiting signatures distinctive from ordinary neutron stars. While these candidate objects are compelling, it is crucial to emphasize that none of them provides conclusive evidence. The observed anomalies could be explained by more mundane neutron star physics, variations in magnetic fields, or observational uncertainties. The challenges of measuring precise radii, surface temperatures, and masses across vast distances make it extremely difficult to distinguish a quark star from a neutron star. Nevertheless, these objects serve as focal points for research, where detailed observation and modeling could one day confirm the existence of quark stars. In essence, candidate quark stars are already hiding in plain sight, quietly masquerading as neutron stars. Their unusual properties, whether it's compactness, thermal behavior, rotation rate, or emission patterns, offer tantalizing hints of the exotic physics occurring within. With the next generation of telescopes and gravitational wave observatories, these candidates may eventually reveal whether quark stars are real, or if their mysteries lie elsewhere. The study of candidate objects also opens the door to exploring how a quark star's surface might differ from a neutron star's, another factor that could provide observational clues. Understanding the unique nature of a quark star's exterior could be key to finally confirming their existence. One of the most fascinating and unusual aspects of quark stars lies in their surface composition, which may be dramatically different from anything we see in ordinary neutron stars. While neutron stars generally have a thin crust of atomic nuclei or neutron-rich material overlaying a dense neutron core, quark stars could, in theory, possess bare quark matter exposed directly to space, or at most, a very thin layer of conventional matter. This distinction has profound implications for both the star's physical behavior and its observational signatures. In a neutron star, the surface is composed of a crust only a few hundred meters thick relative to the star's radius, consisting of nuclei embedded in a sea of electrons. This crust plays a crucial role in shaping thermal emissions, magnetic field interactions, and pulsar activity. It is the barrier that insulates the dense neutron interior from the vacuum of space. Quark stars, however, could lack such a substantial crust. If quark matter extends all the way to the surface, the star would essentially have no conventional matter on top, just a bare quark surface. A bare quark surface would have extremely different physical properties compared to a neutron crust. For instance, the density at the surface would remain extraordinarily high, millions of tons per cubic centimeter, or more. Instead of a gradual transition from dense matter to near vacuum over a crust, the surface of a quark star might feature an abrupt boundary, with matter transitioning directly from quark matter to space. This could influence radiation in several ways. Thermal emissions could deviate from typical blackbody behavior, producing unusual X-ray or gamma-ray spectra. A bare quark surface could also affect the star's cooling rate, allowing heat to escape more efficiently than through a neutron crust. Magnetic field interactions would also differ. Neutron stars' crusts play a role in anchoring and shaping magnetic fields, but in a quark star, the fields might interact directly with quark matter. This could result in stronger or more irregular magnetic field configurations, potentially explaining some unusual pulsar behaviors or gamma-ray flares observed in certain compact objects. Moreover, the quark matter itself may conduct or respond to magnetic flux differently than a neutron crust, creating electromagnetic phenomena unique to quark stars. Some models propose that a thin crust of ordinary matter might still exist on top of the quark core, but it would be extremely fragile and thin, perhaps only a few centimeters thick, due to the enormous density of the underlying quark matter. Even this minimal crust would be subject to intense gravitational and electromagnetic stresses, meaning it could be periodically stripped or redistributed. In extreme cases, the quark surface could be completely exposed, with no traditional matter remaining at all. Another intriguing feature is the possibility of strange quark matter at the surface. If strange quarks are present, the quark star's surface could consist of a highly stable mix of up, down, and strange quarks. This strange matter surface might be so stable that it does not decay or interact with normal matter easily, adding another layer of uniqueness to the star's external properties. In theory, a tiny fragment of strange matter could even persist in interstellar space if ejected from the star, though detecting such fragments would be extremely challenging. From an observational standpoint, the surface composition has direct consequences for astronomers trying to distinguish quark stars from neutron stars. The thermal spectrum from a bare quark surface could be subtly different, with harder X-ray emission or unusual spectral lines. The absence of a thick crust could influence starquakes or magnetic flares, potentially producing bursts of radiation distinct from standard neutron star activity. Even the star's rotation could interact differently with its magnetic field if the surface lacks conventional matter, affecting pulsar timing measurements. In essence, the surface of a quark star represents a window into the exotic interior. While neutron stars have a protective crust separating their dense cores from the vacuum, quark stars may offer direct contact between the universe and matter in its most fundamental form. This surface difference is not just a curiosity. It is potentially one of the most practical ways to detect these elusive stars, by examining X-ray spectra, thermal emissions, and pulsar behaviors for deviations from neutron star norms. The nature of a quark star's surface also reinforces their role as extreme laboratories of physics. If such a star exists with a bare quark surface, it would expose quark matter directly to conditions we cannot replicate on Earth, providing a natural experiment in the behavior of fundamental particles under enormous gravitational and magnetic stress. Understanding the surface thus offers both a potential observational signature and a pathway to probing physics at scales otherwise inaccessible. The extraordinary surface properties lead naturally into the broader view of quark stars as extreme physics laboratories, where the interplay of quantum chromodynamics, gravity, and electromagnetic forces can be studied on a cosmic scale. This is where theory meets potential reality, offering insights into both the universe's most exotic objects and the fundamental laws that govern them. Quark stars, if they truly exist, are among the most extraordinary natural laboratories in the universe, offering physicists a chance to test the laws of physics under conditions that are utterly impossible to replicate on Earth. At the heart of this extreme laboratory lies quantum chromodynamics, QCD, the theory that describes the strong nuclear force binding quarks together inside protons and neutrons. Understanding quark stars allows us to explore QCD in regimes of density and pressure that far exceed those achievable in terrestrial particle accelerators. On Earth, the strongest recreations of quark matter occur in high-energy particle collisions at facilities like CERN's Large Hadron Collider or the relativistic Heavy Ion Collider. These collisions create a fleeting quark-gluon plasma, where quarks and gluons momentarily break free of confinement. However, these states exist for mere fractions of a second, at extremely high temperatures but low densities, vastly different from the cold, ultradense quark matter theorized in quark stars. In contrast, quark stars could maintain a stable, dense state of quark matter over billions of years, giving us a permanent, large-scale natural system to study the behavior of quarks under conditions where pressure, not temperature, dominates. The interior of a quark star is a regime of physics where quark degeneracy pressure and strong interactions reach extremes. Here, QCD is not just a theoretical framework, it governs the entire structure of the star. Properties such as the star's mass-radius relationship, maximum mass, cooling rates, and magnetic field interactions all depend sensitively on how quarks interact at ultra-high densities. By observing quark stars, or even candidate objects with quark matter cores, astrophysicists can test the predictions of QCD in ways that no laboratory experiment could. Essentially, the universe has created a super collider on a cosmic scale, holding quarks together in ways that expose the subtleties of the strong force. Quark stars could also illuminate the behavior of strange quark matter. If strange quarks are present, as theorized in certain quark star models, this introduces additional complexity into QCD. Strange quarks may make the matter more stable and alter the star's thermal evolution, rotational dynamics, and surface properties. Observing these phenomena would provide direct evidence about how quarks of different flavors interact under extreme conditions, testing our understanding of particle physics in a realm far beyond human-made experiments. Moreover, quark stars offer a unique testbed for extreme gravitational physics combined with quantum effects. Their incredibly compact mass creates gravitational fields billions of times stronger than Earth's, curving spacetime significantly near the surface. This combination of ultradense matter and strong gravity allows physicists to probe the interplay between quantum forces, quark interactions, and general relativity, a regime often referred to as strong field QCD in curved spacetime. In other words, quark stars allow us to explore the union of quantum mechanics and gravity in ways otherwise unimaginable. Another aspect of this natural laboratory is the opportunity to study transport phenomena in quark matter. How does heat move through quark matter? How do magnetic fields interact with quark currents? How do neutrinos escape from such a dense, exotic interior? The answers to these questions inform both astrophysics and fundamental particle physics, potentially improving our understanding of matter in extreme environments, from the early universe to neutron star mergers. Quark stars could also provide insight into phase transitions in dense matter. Just as water freezes into ice or boils into steam, matter under extreme pressure may undergo transitions between neutron matter, quark matter, and possibly strange quark matter. Observing phenomena such as sudden cooling events, gamma-ray bursts, or unusual pulsar glitches could provide indirect evidence of such transitions, giving physicists a real-world example of QCD phase changes on a stellar scale. Finally, quark stars help bridge the gap between astrophysics and particle physics. They are cosmic-scale experiments that operate where human technology cannot. Every quark star, if identified and studied, would be a natural observatory for fundamental forces, particle interactions, and matter stability, allowing researchers to test theoretical predictions with real astrophysical objects rather than relying solely on simulations or laboratory analogues. In short, quark stars are the ultimate extreme physics laboratories, ultra-dense, ultra-compact, and dominated by fundamental forces at their limits. They offer a glimpse into a universe where quarks form bulk matter, strange matter may stabilize, and the strong nuclear force dictates the structure of entire stars. By studying these objects, we could unlock a deeper understanding of matter, forces, and the behavior of the universe under conditions that challenge the very foundations of physics. The presence of such extreme laboratories also hints at their broader impact. If quark stars exist, they could reshape our understanding of cosmology and the evolution of the universe, influencing models of early star formation, matter stability, and even the behavior of the densest remnants of stellar collapse. This leads naturally into the next topic, the impact of quark stars on cosmology. Quark stars, if they exist, could profoundly reshape our understanding of cosmology, offering insights that extend far beyond the life cycles of individual stars. Their existence would not just add a new category of stellar objects, it would force us to rethink the very principles of matter stability, the behavior of the early universe, and the ultimate fate of massive stars. At the most fundamental level, quark stars challenge our understanding of matter stability. Ordinary matter, composed of protons, neutrons, and electrons, is generally considered stable under normal conditions. Neutron stars push this stability to its limits, compressing neutrons until they are nearly touching. Quark stars, however, suggest that matter can exist in an even denser, more stable form under extreme pressure, quark matter, and potentially strange quark matter. If strange matter is indeed more stable than nuclear matter, it could alter our assumptions about the ultimate ground state of matter in the universe. In theory, this might even imply that some forms of matter we consider ordinary could transition to more exotic states under extreme conditions, fundamentally reshaping the landscape of particle physics. Quark stars also offer a window into the physics of the early universe. During the first microseconds after the Big Bang, the universe existed in a state of quark-gluon plasma, where quarks and gluons roamed freely before cooling and condensing into protons and neutrons. Quark stars may represent a frozen relic of these primordial conditions, preserving a large-scale version of the quark-gluon plasma. Studying their properties, density, temperature, cooling rate, and magnetic behavior, could provide indirect evidence about how matter behaved in the earliest moments of cosmic history, offering insights into phase transitions that shape the formation of atoms, stars, and galaxies. In a sense, quark stars are cosmic fossils, capturing a state of matter that dominated the universe before ordinary nuclei even existed. The existence of quark stars would also impact our understanding of stellar evolution. Conventional models suggest that massive stars collapse into neutron stars or black holes, with neutron stars representing the endpoint of matter under extreme compression that does not exceed the Tolman-Oppenheimer-Volkoff limit. Quark stars introduce a new pathway, a middle ground between neutron stars and black holes, where the collapsing core transitions to quark matter rather than forming a singularity. This could revise the predicted distributions of compact stellar remnants in the universe, influencing our expectations for supernova outcomes, neutron star mergers, and even gamma-ray burst progenitors. For instance, some short gamma-ray bursts may be powered not by black hole formation but by the sudden birth or collapse of a quark star, changing our interpretation of these high-energy events. In addition, Quark stars could play a role in cosmic matter distribution. If strange quark matter is stable outside of stars, as some theories suggest, fragments of it, so-called strangelets, might exist in interstellar space. These exotic particles could subtly influence galactic chemical evolution or even provide a mechanism for seeding the universe with ultra-dense matter in ways we have not yet considered. While speculative, the idea that quark stars may contribute to the population of exotic matter in the cosmos highlights their potential significance beyond their immediate stellar environment. Quark stars might also provide insight into the ultimate fate of matter in extreme gravitational fields. Black holes represent the endpoint where matter and information are trapped behind an event horizon. Quark stars, being stable yet extremely compact, demonstrate that matter can resist complete gravitational collapse under certain conditions. This may inform theories about the interplay between gravity, degeneracy pressures, and fundamental particle interactions in regimes approaching black hole formation. In this way, quark stars illuminate a subtle but crucial stage in the continuum from ordinary stars to black holes. From a cosmological perspective, quark stars could also have implications for observational astrophysics. Their unique density, cooling behavior, and emission spectra could subtly influence galactic X-ray backgrounds, gravitational wave signals, and the apparent population statistics of compact stars. By identifying and modeling quark stars, astrophysicists could refine simulations of galaxy evolution, binary star interactions, and the high-energy transient universe. This could improve our ability to interpret data from X-ray observatories, gravitational wave detectors, and future telescopes, ultimately enhancing our understanding of the universe at both local and cosmological scales. In summary, the impact of quark stars on cosmology is profound. They challenge our understanding of what constitutes stable matter, provide a rare glimpse into early universe conditions, offer a new pathway in stellar evolution, and may subtly influence cosmic matter distribution and high-energy astrophysical phenomena. Confirming their existence would extend the frontiers of both particle physics and cosmology, revealing that the universe holds forms of matter and physical states far stranger and more extreme than previously imagined. From here, it is natural to explore how quark stars connect to black holes, as they occupy the precarious threshold between stability and ultimate gravitational collapse, offering unique insight into the continuum of stellar death. Quark stars occupy a fascinating and precarious place in the cosmic landscape, sitting at the very threshold between neutron stars and black holes. Unlike black holes, which are defined by the presence of an event horizon and the collapse of matter into a singularity, quark stars are compact objects where matter has been pushed to extreme densities but remains stable against complete gravitational collapse. This makes them a sort of middle ground in stellar evolution, illustrating the delicate interplay between fundamental forces and gravity. To understand this connection, it helps to consider the life cycle of a massive star. When a star exhausts its nuclear fuel, it can no longer support itself against gravity. Low to intermediate mass stars form white dwarfs, higher mass stars form neutron stars, and the most massive ones collapse into black holes. Neutron stars themselves are already extreme. They pack solar masses into a sphere barely 10 to 20 kilometers across. The question becomes, what happens if a neutron star exceeds the Tolman-Oppenheimer-Volkoff (TOV) limit, the maximum mass a neutron star can sustain without collapsing into a black hole? Quark stars may provide the answer. If a neutron star's core is pushed just beyond the threshold where neutrons can resist collapse, the degeneracy pressure of neutrons alone may not suffice. Under these conditions, neutrons could dissolve into quark matter, forming a quark star. This new state of matter, composed of up, down, and potentially strange quarks, can resist further compression more effectively than neutrons alone. In this sense, quark stars act as a buffer between neutron stars and black holes, preventing immediate collapse while existing at densities approaching the theoretical limit for stable matter. The proximity to black holes is striking. Quark stars are often only a few kilometers smaller in radius than neutron stars of similar mass but much denser. A quark star packing two solar masses into a sphere only about 10 kilometers across has a surface gravity and space-time curvature approaching that of a black hole, yet it still supports itself against complete collapse due to the pressures generated by quark matter. Essentially, quark stars are gravity's nearly ultimate challenge, demonstrating how far matter can resist collapse before succumbing to the formation of an event horizon. Another key difference is that, unlike black holes, quark stars have a physical surface. While the interior is exotic, composed of quark matter, it still maintains a boundary separating it from the vacuum of space. Black holes, by contrast, have no surface in the traditional sense. The event horizon marks a point of no return, and the singularity within contains all the mass, compressed to an undefined density. Quark stars, therefore, provide a unique observational window into matter at densities close to those inside black holes, but with detectable electromagnetic emissions, pulsations, and potentially gravitational wave signatures. In terms of formation scenarios, quark stars may represent a temporary or permanent stage in the evolution toward black holes. In some neutron star mergers or supernovae, a hypermassive neutron star may briefly form. If conditions are right, quark matter could emerge in the core, creating a quark star that stabilizes for a period before collapsing further. In other cases, the star may remain a quark star indefinitely if its mass is below the threshold for black hole formation. This makes quark stars a critical missing link in the continuum of compact objects, showing how matter transitions from neutron-degenerate matter to quark-degenerate matter and eventually to complete gravitational collapse. Quark stars also illustrate the physics of extreme equation of state behavior. The equation of state, EOS, describes how matter responds to pressure and density. For neutron stars, the EOS is constrained by nuclear physics, while for black holes, the EOS is essentially irrelevant once the singularity forms. Quark stars occupy the middle ground, where the EOS of quark matter is critical in determining whether the star survives or collapses. Observing quark star candidates and measuring their mass-radius relationships can therefore provide valuable constraints on ultra-dense matter physics and the transition between stellar remnants and black holes. Finally, quark stars help us conceptualize the limits of observable physics. Black holes mark a point where all information about the interior is hidden behind the event horizon. Quark stars, however, push matter to nearly that limit but remain observable. They are cosmic laboratories at the edge of collapse, offering insight into the behavior of matter under conditions that bridge the gap between theory and the otherwise inaccessible interiors of black holes. In essence, quark stars are the universe's ultimate middle ground objects. They are denser and smaller than neutron stars, teetering on the edge of gravitational collapse, yet resisting transformation into black holes thanks to the exotic properties of quark matter. Studying them allows scientists to explore the continuum of compact objects, connecting the well-understood world of neutron stars to the mysterious, information-concealing realm of black holes. From this understanding of their connection to black holes, it becomes clear why quark stars remain hypothetical. They are incredibly challenging to detect, their observational signatures can mimic neutron stars, and their formation occurs only under very specific conditions. These challenges naturally lead into the next discussion: why quark stars have not yet been conclusively observed. Despite decades of theoretical work and tantalizing observational hints, quark stars remain firmly in the realm of hypothesis. One of the primary reasons is that current observational tools are limited. Even our most advanced telescopes and space-based instruments struggle to measure the precise properties, such as radius, mass, and surface composition, required to definitively distinguish a quark star from a neutron star. The differences between the two can be subtle: a few kilometers in radius, slightly faster rotation, or marginally different thermal spectra. Observational uncertainties of even a few percent can obscure these distinctions, making it difficult to confidently identify a quark star. Another major obstacle is distance. Most candidate quark stars are hundreds or thousands of light-years away, making their signals faint and often distorted by intervening interstellar material. X-rays and gamma rays can be absorbed or scattered by cosmic dust and gas, while electromagnetic emissions may be blended with background sources. Even when pulsars provide highly regular signals, the slight variations that might indicate a quark star's presence can be overwhelmed by noise from other astrophysical processes. The similarity of quark stars to neutron stars further complicates matters. Many of the theoretical signatures, rapid cooling, unusual X-ray spectra, gamma-ray bursts, or pulsar glitches, can also be produced by conventional neutron stars under certain conditions. For instance, a neutron star with a particularly strong magnetic field, rapid rotation, or an atypical crust may mimic the expected emissions of a quark star. Distinguishing between subtle deviations caused by exotic quark matter and variations in ordinary neutron star behavior is therefore extremely challenging. Moreover, formation conditions for quark stars are likely rare and finely tuned. A neutron star must reach a precise combination of mass, density, and pressure to convert to quark matter without immediately collapsing into a black hole. This means that quark stars may be inherently uncommon, so even if they exist, the chances of observing one in a nearby, accessible region of space are small. Many potential quark stars may simply be too distant, too faint, or too few in number for us to detect with current instruments. Gravitational wave observations, which might reveal quark stars through mergers or unusual tidal effects, also face limitations. While LIGO, Virgo, and other detectors can detect the ripples from neutron star collisions, distinguishing subtle differences between a merger involving quark matter and one involving ordinary neutron stars requires extremely precise measurements. Current sensitivity levels may not yet be sufficient to confidently separate these signals. Another issue is theoretical uncertainty. The properties of quark matter under ultra-dense conditions are still poorly constrained by quantum chromodynamics and related models. Small differences in the assumed behavior of quarks at high densities can lead to large differences in predicted mass, radius, and cooling behavior for quark stars. This uncertainty makes it difficult to produce definitive observational tests, since we cannot yet say with absolute confidence what a quark star should look like. Finally, the transient and violent nature of some candidate signatures complicates observation. Events such as sudden gamma-ray bursts, quark phase transitions, or crust rearrangements may be brief and unpredictable. Capturing these events requires continuous monitoring of vast regions of the sky, which is not always feasible. Even when a transient is detected, distinguishing a quark star origin from other astrophysical phenomena, such as neutron star mergers, magnetoflares, or accretion events, is extremely difficult. In combination, these factors, instrumental limitations, extreme distances, subtle differences from neutron stars, rarity of formation, theoretical uncertainties, and transient phenomena, mean that quark stars remain hypothetical. Every potential signal is ambiguous, and even the best candidate objects, like RxJ 1856.5-3754 or certain unusual pulsars, could plausibly be explained without invoking quark matter. Until we obtain more precise, multi-channel observations or detect an unmistakable signature uniquely attributable to quark stars, their existence remains unconfirmed, a tantalizing possibility that pushes the boundaries of astrophysics and particle physics alike. Despite these challenges, ongoing improvements in technology and observational methods promise that the mystery of quark stars may not remain unsolved forever. Future telescopes, gravitational wave detectors, and high-energy observatories may provide the conclusive evidence needed to reveal these exotic stellar objects and finally move them from theory into reality. The search for quark stars is poised to enter a new era thanks to upcoming and current cutting-edge instruments capable of observing the universe with unprecedented precision. These tools offer hope that, finally, quark stars, if they exist, might be identified through their subtle and exotic signatures. Observatories like the James Webb Space Telescope, JWST, the Neutron Star Interior Composition Explorer, NISA, and advanced gravitational wave detectors represent complementary approaches, each targeting different aspects of these enigmatic objects. JWST, with its extraordinary sensitivity across the infrared spectrum, opens the possibility of measuring thermal emissions from compact stars with a level of detail previously unattainable. While quark stars emit primarily in X-rays due to their high surface temperatures, the infrared observations can help refine models of their cooling rates, surface composition, and surrounding environments. For example, if a compact object is cooling faster than predicted for a neutron star of its age, JWST could detect the corresponding changes in infrared flux, providing indirect evidence for a quark matter interior. Moreover, JWST's high-resolution imaging can help isolate quark star candidates from surrounding stars and dust, reducing background noise that has historically complicated such observations. NISA, mounted on the International Space Station, is specifically designed to probe the X-ray timing and spectroscopy of neutron stars. Its capability to measure pulsations and surface emissions with extraordinary precision allows researchers to infer both the mass and radius of compact objects, two critical parameters for distinguishing quark stars from neutron stars. A quark star, being smaller and denser than a neutron star of comparable mass, would produce subtle differences in X-ray pulsation profiles. NISA can detect these variations, particularly through pulse shape modeling, which constrains the geometry of emission and the star's compactness. By combining timing data with spectral measurements, NASA can help identify candidates whose properties are inconsistent with ordinary neutron stars. Gravitational wave detectors like LIGO, Virgo, and the upcoming Einstein Telescope or Cosmic Explorer provide yet another avenue. Quark stars in binary systems, especially during mergers, could produce gravitational waves with distinct tidal deformability signatures. Tidal deformability measures how much a star's shape is distorted by its companion's gravity, and quark stars, being denser and more compact, would resist deformation differently than neutron stars. These differences subtly alter the waveform of the emitted gravitational waves, particularly in the inspiral phase of a merger. By carefully analyzing gravitational wave signals, researchers may detect evidence of quark matter in the remnant, or even catch a neutron star converting into a quark star during the merger process. High-energy observatories like XMM Newton, Chandra, and future missions such as Athena can also play a role by capturing X-ray bursts, gamma-ray transients, and thermal spectra from candidate objects. Quark stars may display rapid cooling or unusual burst profiles, and observing these phenomena with sensitive instruments could help distinguish them from typical neutron star activity. Observing multiple wavelengths simultaneously, X-ray, gamma-ray, and infrared, enables a comprehensive picture of the star's surface, emission mechanisms, and potential quark core. Another exciting prospect lies in multi-messenger astronomy, which combines electromagnetic observations, gravitational waves, and neutrino detections. A quark star forming during a neutron star merger could produce a combination of gravitational wave signatures, gamma-ray bursts, and neutrino fluxes distinct from conventional neutron star mergers. Coordinated detection across these channels would dramatically increase confidence in identifying quark stars and reduce ambiguity caused by overlapping signatures from neutron stars or black holes. In addition, theoretical modeling and simulations will complement observational efforts. Advances in high-performance computing allow researchers to simulate quark matter behavior under extreme conditions, predict observational signatures, and refine criteria for candidate identification. When combined with data from JWST, NASA, and gravitational wave detectors, these simulations provide a roadmap for recognizing the subtle hallmarks of quark stars. Finally, the synergy of these instruments may be crucial in identifying rare and transient phenomena, such as a neutron star converting into a quark star or a quark star experiencing sudden energy releases. Detecting such events requires continuous monitoring, high time resolution observations, and multi-wavelength coverage, capabilities that modern observatories are increasingly providing. Over the next decade, these tools may finally allow astronomers to confirm or refute the existence of quark stars, transforming a long-standing theoretical concept into a tangible part of our understanding of the universe. In short, future research and advanced telescopes are not just incremental improvements, they represent the first realistic opportunity to observe quark stars directly. By combining precise X-ray timing, thermal spectra, gravitational wave measurements, and multi-messenger signals, scientists may soon have the evidence needed to finally reveal these extraordinary stellar objects and study matter in its most extreme, exotic form. As we reach the culmination of this exploration into quark stars, it becomes clear that these objects, if they exist, occupy a frontier where astrophysics, particle physics, and cosmology converge. From the crushing densities that dissolve neutrons into quarks, to the exotic strange matter that might make up their cores, quark stars challenge our understanding of what matter can be, how stars live and die, and how the universe itself organizes its most extreme phenomena. They occupy a precarious middle ground between neutron stars and black holes, pushing the limits of gravity while remaining observable, offering a glimpse into conditions otherwise inaccessible anywhere in the cosmos or on Earth. Their potential discovery would represent more than just a new type of star. It would confirm a new state of matter, something theorized but never directly seen. We would finally have evidence that the universe can hold matter in configurations far denser, more stable, and more exotic than the neutrons and protons we have studied for over a century. The implications ripple through astrophysics, quantum chromodynamics, cosmology, and even our understanding of the early universe, providing clues about the moments immediately following the Big Bang and the fundamental forces that govern reality. Yet despite decades of research, despite candidate objects, pulsars with odd behaviors, and subtle anomalies in X-ray and gravitational wave data, quark stars remain hypothetical. They remind us that the universe is vast, and our tools, however sophisticated, can only glimpse a fraction of its extremes. Detecting them requires not just advanced instruments, but a synthesis of theory, observation, and interpretation across multiple disciplines. Each potential candidate object challenges us to question what we know, and to consider that the cosmos may contain forms of matter and energy that defy conventional understanding. Ultimately, the search for quark stars exemplifies the essence of scientific exploration, pursuing phenomena at the very edges of knowledge, confronting theoretical possibilities with experimental limitations, and daring to imagine states of matter that test our most fundamental assumptions. If quark stars are ever confirmed, they would serve as cosmic laboratories, teaching us about the strong nuclear force, the behavior of matter at extreme density, and the delicate balance between collapse and stability that governs the life cycle of stars. And so, the mystery remains open, beckoning astronomers, physicists, and curious minds alike. In the quiet depths of the cosmos, among pulsars, supernova remnants, and the dense stellar corpses of massive stars, quark stars may be waiting, hidden in plain sight, their signals subtle but profound. If quark stars exist, they would represent an entirely new state of matter, proof that the universe still hides secrets deeper than imagination. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.